Thank you for inviting me. Can you all hear me? Yes, even in the back? All right, sounds great. Oops. Guys, we're too smart. All right, so today I'm here to represent NVIDIA, to tell you a little bit about the AV program at NVIDIA, and specifically what we're thinking around next gen, so what's coming next. So AV at NVIDIA is really full stack, right? So we produce hardware, meaning in-car chips that are accelerating the software infrastructure, right? With AV, we need massive data, massive training, simulation runs, right, to test the software. So you need the appropriate infrastructure amount of GPUs that scales. Simulation, we don't depend on any external software. It's all in-house, meaning that it's all repeatable, state-of-the-art graphics, fully controllable by us. Drive, so NVIDIA Drive is a product. It's going to launch, I think, next year with L2++, meaning it's going to run autonomy, city, and highway, but human in the loop still, so L2++. And then, of course, there's also research. So research is an important part of NVIDIA, many different topics from generative AI, robotics, graphics, and also AV. And for our next gen, actually, we're all kind of combining forces, which is quite exciting. So hopefully I'll tell you a little bit about that. So if we look at the AV stack evolution through the years or even decades, right? It started with rule-based, more algorithm-focused. Then AI was basically inserted in all the modules, right? From perception to planning. And this is actually what is mostly deployed these days in OEMs in the cars, right? And the future needs to go beyond this, right? It needs to extend the generalization capabilities, meaning foundation models and stacks with as little human engineering as possible. Right, so the AI-enhanced stack is basically what NVIDIA currently has standing up in product. Issues, of course, right? So you have heavy dependency on label data that doesn't really scale. You have limited understanding of complex scenes. Everything, rare cases you almost never collect, right? So it's hard to deal with them. Very short-term system memory, right? Typically have like a window of maybe 1-2 seconds. Meaning, like worst case, if I change lane 5 seconds ago, I don't have a memory of that anymore, which is not great, obviously. And there's a lengthy development because there's human engineering heuristics between every pair of modules, meaning that you have this very slow iteration cycle. So we want to kind of in the next gen, which is mainly what I'm going to talk about today, kind of fix all of this stuff, going towards more scalable and generalizable system. So one thing is just more end-to-end training stacks. I think the community is building or gearing towards that. And foundation models that basically train general knowledge and then fine-tune in domain, basically everywhere in the AV, right? From the stack to simulation, data, maybe even some part of metrics, and of course, any kind of in-cabin assistance. NVIDIA has strong foothold in generative AI. I think just last week we launched the LLM, maybe the biggest, 340 billion with a permissive license, beats a lot of the LLMs out there. Picasso, text-to-image, text-to-3D, and more. It's basically diffusion-based architecture for generating images or 3D. You can go to Getty and Shutterstock. It's already in action. So those features are supported by this architecture. DLSS3, who plays games, RTX on, right? 7 out of 8 pixels are invented by AI. Villa is a captioning, or let's call it a vision language understanding model, released maybe 2 weeks ago, got 1 million downloads in basically a week or two. Best open source model for vision language understanding. So in recognition of that, of course, NVIDIA also building a next-gen hardware on top of the Blackwell GPUs with particular performance improvements for transformers and generative AI, right? So you got like 10x or almost 10x speed up for something like Lava 7B and even CPU is much faster. So it's really gearing towards you guys deploying foundation models in the car, okay? So today's talk, we're gonna talk about 3 different areas, how we're kind of thinking about the role of foundation models in data tooling, really speeding up, how we interact with data, how we're introducing foundation models in the AV stack, and then simulation. That's dear to my heart. So we're going to talk about how AI is kind of transforming simulation and making it more scalable. All right, so foundation models and data tools, right? So you're collecting a ton of data, like massive data, especially once the product is deployed on consumer cars, right? And there's already standard tools that process that data, but now we can go to really the next level, right? We can introduce VLMs, so you can have auto labeling, but open vocabulary, captioning, descriptions of what's going on. We can use that for scenario search, video search, and semantic clustering. You're gonna see some cool examples of that as well. Then, of course, we need to build data tools and incorporate technology, so you can do really powerful image retrieval, video retrieval, more semantic scenario retrieval, and even like 3D open vocabulary labeling. And of course, there's a loop, right? So all these tools are being used by developers to do model training, creating evaluation data sets, as well as for simulation, like replay, or even what we're going to talk about today, going from data to simulation. So we have a pretty powerful visual retrieval, both image and video model deployed. It's currently indexing around almost 40 million video clips, and is basically indexing all ingested data or most of the ingested data per day. Text search, you can also do image video search, and it kind of learns from on-the-fly human feedback as well. So we're estimating that with these kind of features, the developers can just go open vocabulary, a dog walk in the street or something like that, can give you around 30 to 60 speed increase in data sourcing, right? Which was previously mostly, I wouldn't say manual, but definitely very slow. Captioning, we've noticed we're training these big video models as well, maybe not exactly for AV yet. Longer captions are super good for training these performance models. And for AV, this is particularly important. You really want to describe everything that's going on that's relevant to driving. So we're working on video captioning methods. And then using those descriptions to do semantic scenario clustering and retrieval. So here is one example. This is a little bit different than video retrieval. Video would be, a dog is walking the street. Here, you really want to have a scenario, a cut-in. For example, agents from adjacent lanes entering ego lane. So let's look at a couple of examples. You can see the agents actually going into the lane. Another one, this is a slowdown because the vehicle in front has a braking light on. Super useful for testing, right? Because you really want to check that you're handling this kind of hard scenarios. And some kind of earlier research work that allows you to just do, a description of an item you want and then label everything in 3D or find relevant queries. All right, so that was about data. Let's talk a little bit about the stack. I would say that we are still early on, but I'm going to tell you a little bit about what we're thinking and where we are. So we're going with the tokens and transformers architecture. So all the sensors, plus maybe optional contexts such as text or even ego action are tokenized. And then we build basically a large transformer models that encodes that. And this transformer is trained to predict with the generative objectives, so predict the next frames. And we're pre-training on generic images, whatever you can get your hands on, images, videos, and text in terms of modalities, and then fine-tuning on AV data, which means that now you have multi-camera rigs, maybe even other sensors. So there needs to be some adaptation for in-domain processing. Of course, you need to put a driving stack on top, right? So we're decoding parallel heads, so there's no connections between heads, so at least that's the current thinking. of basically standard models. They're just not interconnected. And one thing that actually I'm going to show a little bit later, what we're doing for trajectory prediction, we're going to do human driving, right, which a lot of other people are also working on, because you got like really nice human-like driving. But we're also trying to supervise from simulation. So you want to have rollouts, and you want to kind of teach the model to not break rules and to be safe and comfortable. And of course, there needs to be safety monitors and guardrails that make sure that we are actually deploying a safe system. All right, so we're kind of drawing the inspiration for this stack from various research results that are going to be presented here at CVPR. We had access to them many months before. So ParaDrive by Marco Pavone's team is essentially doing a search over all possible connections between these modules. And they found that if you just do parallel decoding, you're getting like a much lower collision rate. So you get a safer system as well as much faster system. Super awesome work. Jose, where are you, Jose? Invented this Hydra-MDP that basically says that if we use this rollout in simulation as a teacher for these other losses, safety-informed losses, well, you can win a benchmark on it, apart from other innovations in the architecture. So there's this end-to-end challenge leaderboard, and Hydra-MDP by Jose and team actually won by 5%, which is significantly. So we're celebrating that today. We also had this work that was focused on behavior modeling, but we're going to go with this kind of approach. It basically represents output trajectories as discrete tokens, and then again, transformer is autoregressively decoding them. And this has been shown, at least for the behavior modeling, to surpass state of the art, at least at the time when we released it. And we checked a couple of days ago, and all top performers actually follow this paradigm. Super powerful architecture. The really key is going to be how to make this real time to run in the car. And we have quite some good results on that already. The backbone is currently where we're putting the most attention, right? I talked about video generation as a pre-training task, so you can actually consume all this massive data, both on the internet and internal data. And we built quite a muscle on this already, right? So we had one of the first world models that was in 2020. And then 2023, which is basically a year ago, was the first latent diffusion model. We introduced Sora, and stable video model is basically based on top of this kind of architecture, obviously more advanced with transformers instead of UNet. At the time, so this was already a year ago, we were kind of looking at this model, and then we found some really nice emergent properties. One is compositionality, right? Because we're kind of interested in AV. So we were testing just by training on internet, how much compositionality can we get actually for relevant for driving? Can we put an elephant or a dog with like VR goggles on the street? And the answer is actually yes. There's quite a bit of camera and motion control you get like as an emergent properties of this model, but just a little bit of fine tuning. So you can see that little frog is being rotated if we just keep the right prompt and controlled by just motion and no camera. So all this kind of gave us the belief that there's so much knowledge, there's compositional knowledge, and there's 3D understanding in these models that we should be able to exploit. So we've been kind of working on that for as a backbone now for AV. So one of the first thing was just maybe improving the architecture and then fine-tuning the pre-trained, like world pre-trained model on internal data. And the results were quite surprising because first of all, it's very stable temporally. It can handle some really nice effects such as rain, snow. None of this was actually part of the data that we fine-tuned the model on. We fine-tuned it on about 2,000 hours of data. We didn't have those examples. And it even creates an accident on top right. We had no single example of an accident in our training data, meaning that the model is really kind of learning the sensors, the intrinsics of the internal sensors, but bringing all that knowledge from the internet here. And this is exactly what we want. I don't necessarily care about pretty pixels. We care about understanding the capabilities of these models, okay? Pretty pixel is an afterthought, maybe for simulation. The next was extending it, right? The rig actually has more cameras. So now we can do 3 cameras. That's the next attempt. Just kind of look at the consistency between the camera. That's what you should be noticing. There's a snowman in the query, both in front and the top right camera. It looks consistent. This car, as it drove here, it kind of casts a shadow into this camera. It looks pretty nice and consistent. Here's one more example. Even the sun is kind of consistent across the different cameras. And just now, I would say this is earlier results, 6 cameras, which is the rig we're going to be going with. This started to present more challenges because now you can't really fit this anymore into a GPU. So there's some compromises we're making here. So maybe the quality is not quite yet there. But definitely we're seeing a lot of consistency across the 6 camera generation. And of course, for deploying this in the car, you need that. Some funny challenges here that we still need to, basically means more scaling. Right now, we really haven't scaled this model yet. We're still in development. Just kind of look at this green box over here. There's going to be some inconsistency, some cyclist or motorcycle appearing and then disappearing. He just hasn't seen enough, motorcycles, doesn't really understand yet how they behave. So some physics is still not there. But we think that can be solved by scaling or at least addressed. One thing for those that you're developing these models, video tokenization, how you actually tokenize the frames or the video of the video clips, is pretty much the most important thing when you're developing these models. Right, because a transformer is basically sitting on top of these tokens. If the pillar is not good, then nothing on the top can compensate for it. So fewer tokens means that you would be faster in the car, right? But at the same time, fewer tokens also means lower construction. So if you look at the left, the text is gone, it's kind of all muffled up, right? If you start introducing discriminative losses in the token reconstructions, not just reconstruction, but discriminative losses, which typically what people do, the pixels start looking better, but the model starts hallucinating, okay, which is actually not what we want for driving. Maybe for generation, that's good, but for driving, we cannot basically, look at this example, right? The input was a green light, and the model turned into a red light. So you really need to be careful how you train these tokenizers. One of the most important things when you're training these models. All right, so now basically, we have a pretty powerful foundation. The backbone, we're still obviously improving it. But we kind of already want to put like a policy head on top, trajectory, and just seeing whether you can drive on it. If not for anything else, just to see as a metric of how good these videos models actually already are and where the gaps are, how we need to scale them further. So here on the left is just a short snippet, and the last frame is basically where we're going to be predicting a trajectory, and the video is encoded with basically this video model. This is ground truth. This is where the car actually drove, and this is what the model is predicting. So it's kind of interesting, for example, here, because we're not conditioning on the goal yet. It's kind of seeing that it could go straight, but also turn right. And here it's predicting correctly there's a turn. And so the color here, the more yellow means higher up, so higher elevation. It's actually predicting that we are moving upwards, which is pretty awesome. All right, so this is open loop, all right? But obviously for testing, even for development, we want to have a simulation in the loop. We want to be developing this model in simulation, especially as we're going more towards end-to-end models, right? Where we cannot break it up into components as easily. We really need to think about powerful simulation tools. So at NVIDIA, we have 2 different approaches plus a hybrid. One is, let's call it more traditional graphics-based. So full real-time physics, ray tracing, and physics simulation. Perfect for hardware in the loop, so integration testing. There's also scalable environments, but still the content is relatively limited, I would say. And then because we want to have this fast iteration cycle, so as soon as you find an issue on the road, ideally you would quickly check whether you have actually corrected it. So we need something that kind of closes the domain gap, right? If you went directly into the graphics engine, you're never quite going to be matching what you recorded. So we're also looking into reconstruction methods, and this is already a simulator in production. And of course, the hybrid model, the hybrid simulators that exploits both traditional graphics and neural graphics. All right, so let me show you a little bit about the simulation capabilities. Specifically, I want to focus here on this hybrid simulator. So the environment is reconstructed, neural techniques, NERF, and all the objects here are going to be inserted, full physics, and that's exploiting the Omniverse features. You can see kind of, I don't know whether you see, but the cars are kind of bumping on the road. We reconstruct traffic lights, inserts in synthetic traffic lights, so we have perfect control of the traffic, can test different scenarios. With Omniverse, we inherit great physics. We can put the fire on the truck, you know, collisions, damage, and smoke. Can also deal with dynamic reconstruction, obviously, scenes or scenarios, or the real world is dynamic. So this is basically showing that the scene is not playback, is actually reconstructed. Or here is a constructed. In some of the scenarios, you're going to see a little bit of bumpiness, which is going to reveal that it's still not as perfect. But this is already in production now. We're running tests against the simulator. And you can use this also to do scenario editing. So just four versions of the same scenarios. It's kind of notice there's kind of variation. We can swap and replace the cars into this different rollouts. All right, so that was kind of the simulation. We talked about the AV stack. Now let's put them together just so that you guys see some, you know, first rollouts of these models in this neural simulator. So in the top, let's look at that first. So is this, you know, generative pre-trained video backbone with a trajectory on top, currently only driving this car. So it kind of correctly slow down and turn right. Here it's going to handle a pretty complex intersection, which is quite exciting. Here we're doing multiple rollouts. We're just going to be sampling from the model, just seeing how the, you know, what are plausible futures. It's going to be a pedestrian that pops up here. So the car is going to correctly actually change lane. And in different rollouts, it's going to change the different lanes, which is pretty awesome to see. One more example. One decided to park and one decided to drive. Okay, last one. Slowing down. Here, one rollout decided to go straight where the original capture was done. One decided to go right, and then we're kind of running out of the world. So you see like bad reconstruction here. So here is where generative AI perhaps is gonna help in the future. I showed object insertion because really kind of, yes, you reconstruct the world. Yes, you want to have exactly the same scenario, maybe interactive, but you also want to put a whole bunch of distractors and actually check that the car is doing what you want it to do. So object insertion and the quality of that is super important. I already showed that in the beginning, but we're really working towards improving those, you know, the quality. So top was kind of the most basic result, and the bottom is kind of our current result, which is much more realistic. Here is just like one example. You can handle night and different lighting condition. Looks very realistic. All the assets are synthetic here. Secondary effects, we can now do ray tracing with these neural representations. Again, super important so that there's as little gap with reality as possible to really test these vehicles. And the other one is just scale, right? So in autonomous driving, especially if you're in a highway, you know, 20 seconds, 30 second scenarios can quickly be kilometers. And if you check any of these neural approaches, they typically kind of like run out of capacity 100 to 100 meters. right? So you need to make sure that you're able to reconstruct much, much larger environments and in a consistent manner. Okay, some 3D generation. Like I said before, we kind of run out of the world. So we need to equip ourselves with some generative capabilities. And AV, especially simulation, is about large worlds. Our world is really large, right? So when you're driving, even that, you probably want to see 200 meters ahead. So typically people put a lot of heuristics of where they're going to put their capacity. I'm quite excited. So we're going to release this machine learning framework that handles really large-scale spatial intelligence at SIGGRAPH. And it's really leveraging the power of graphics. It's using this data structure called VDB and putting all the machine learning operations on top of that. And we can do quite amazing things with it. So that's going to be all open sourced.
The real world is large, and we want to create digital twins at the scale of reality. To do this, we need to build algorithms that scale to the size of reality. Algorithms like city-scale neural radiance fields, and algorithms like mesh reconstruction from 1 billion LiDAR points. The main bottleneck to building these algorithms is deep learning infrastructure. We need infrastructure that can handle large spatial scale to capture the size of the world. We need infrastructure that can handle high resolutions to simulate the fine details of the world. And we need infrastructure which can be distributed on multiple GPUs to leverage computation at scale. To address these infrastructure needs, we've developed fVDB, a deep learning framework for sparse, large-scale, and high-performance spatial intelligence. fVDB enables many useful applications, such as reconstructing a triangle mesh from 1 billion input points, building and rendering neural radiance fields at the scale of cities, building generative models for large spatial scale data, and enabling high-resolution simulation with deep learning.
Yeah, so that's hopefully going to enable all of you guys to have much, much more fine-grained and large-scale perception, simulation, whatever you're building. VDB is this data structure that's actually the inventor of VDB has been working on this. That's Ken Musset. He just got an Oscar for that. Pretty cool. All right, so summary, kind of I said NVIDIA's full stack, we're building hardware, we're moving toward generative AI, and it's really research and product working together, super exciting. In this kind of phase development, agenda. Advanced simulation tool, and I didn't talk more about safety today, but there's a lot of effort going into online monitoring, guardrails, and of course large-scale testing. Yeah, and I'm very excited about this because it's really multiple research teams stepping together and working with product, and this is really the culture of NVIDIA. We win by being one team. So thank you very much.